Hey guys, Lainey here, and today I will be presenting two peer-reviewed journal case studies that focus on foundation interaction and deep excavation effects in urban environments. Both papers document real-world performance of geotechnical systems and highlight how interaction effects can significantly influence settlement behavior, whether between adjacent foundations or between excavations and existing structures. The two articles I selected are a 2023 paper by Harry Poulos on settlement interaction among multiple high-rise buildings, and a 2023 case history by Yang and co-authors examining deep excavation effects on adjacent bridge piles in a karst region. The purpose of this presentation is to summarize each article and explain why the case studies are relevant to engineering practice, describe the analytical and observational methods used by the authors, highlight the key findings and practical lessons learned, and reflect on what I found most interesting and how these papers connect to concepts from this course. The first article is titled Analysis of Foundation Settlement Interaction Among Multiple High-Rise Buildings by Harry Poulos. This paper is motivated by the increasing density of urban development, where high-rise buildings are often constructed very close to one another. Poulos refers to these settings as high-rise urban forests. While wind and seismic interaction between nearby buildings is well studied, foundation design often still assumes that each building behaves as a standalone system. However, field observations suggest that adjacent foundations can influence settlement through the soil. The purpose of this study is to understand how significant that interaction can be and to provide a simplified method that helps engineers evaluate interaction effects without performing complex three-dimensional numerical analyses. From an engineering perspective, the buildings considered in this study are supported on deep foundations, typically pile groups. Rather than modeling each pile individually, Poulos uses an equivalent pier approach. In this method, the entire pile group, pile cap, and enclosed soil mass are represented as a single pier with equivalent stiffness. The subsurface profile is idealized as a layered soil system, commonly consisting of a softer upper layer over a stiffer bearing stratum. This is representative of many urban sites supporting high-rise construction. The primary engineering problem addressed is how settlement of a building evolves as surrounding buildings are constructed and loaded, particularly when the construction occurs in stages rather than simultaneously. To study these interaction effects, Poulos performs axisymmetric finite element analysis using Plaxis. The foundation of interest is modeled as a central equivalent pier, while surrounding buildings are represented as concentric smeared pier rings. This approach allows multiple nearby foundations to be simulated within a simplified axisymmetric framework. Typical parameters used in the analyses include equivalent pier diameters of approximately 50 meters, pier lengths ranging from 20 to 40 meters, and applied pressures of about 300 kilopascals, which are representative of multi-story building loads. Based on these numerical results, Poulos develops settlement interaction factors that quantify the additional settlement induced at one foundation due to loading of adjacent foundations, as a function of spacing and relative stiffness. One of the most important findings of this study is the magnitude of settlement interaction effects. In several cases, the settlement of the central foundation increased dramatically after surrounding foundations were loaded. For example, settlement increased from approximately 75 millimeters under the building's own load to over 200 millimeters once nearby buildings were constructed. The study also shows that interaction effects are especially pronounced when surrounding foundations are shorter or less stiff than the central foundation. In these cases, the stiffness contrast causes greater load redistribution through the soil. A key practical takeaway is that the stiffness of adjacent foundations can control settlement behavior more than the properties of the building being evaluated. This has major implications for staged urban construction. The second article is titled Performance of a Deep Excavation and the Influence on Adjacent Piles by Yang and co-authors. This paper represents a detailed case history of a deep excavation for a metro station in Guangzhou, China, constructed near an existing bridge. The project site is located in a karst region with highly variable subsurface conditions, including soft clay, sand layers, karst cavities, and confined groundwater. This case study is particularly important because it combines extensive field monitoring with numerical back analysis to clearly identify the mechanisms responsible for unexpected settlement of nearby bridge piles. The metro station excavation had a depth of approximately 18 meters and was supported by 1 meter thick diaphragm walls. The retaining system included multiple levels of internal bracing using reinforced concrete struts at upper levels and steel struts at deeper levels. An existing bridge supported on cast-in-place board piles was located approximately 18 meters from the excavation. Some of these piles were founded in soft clay rather than in bearing on rock. The main engineering concern here was whether excavation-induced soil movement and groundwater changes would cause excessive settlement or damage to the existing bridge foundation system. This project relied heavily on field observations to track system performance. Monitoring included inclinometer measurements of wall and soil movement, ground surface settlement points, groundwater monitoring wells, and precise level measurements on bridge piles. During excavation, significant groundwater inflow occurred, leading to the use of the MetroJet system grouting method to control water ingress. This intervention itself caused additional soil disturbance. To supplement field data, numerical analyses were performed using Plaxis 2D with the hardening soils small strain model, allowing the authors to capture both stress-dependent stiffness and small strain behavior. Field measurements showed that maximum diaphragm wall deflections ranged from 0.13 to 0.30% of the excavation depth, with an average of about 0.2%. These values were consistent with empirical prediction methods. However, the most significant finding involved the nearby bridge piles. Settlements reached values of up to approximately 36 millimeters, and settlement rates more than doubled during excavation. Initial numerical models that neglected confined groundwater significantly underestimated both ground surface and pile settlements. When confined water drawdown in the sand layers was included, model predictions closely matched observed behavior, demonstrating that groundwater withdrawal was the dominant settlement mechanism. Although these case studies address different problems, they share several common themes. The Poulos paper focuses on interaction between adjacent foundations, while the Yang paper focuses on interaction between excavation, soil, groundwater, and existing foundations. Both studies show that construction sequencing is critical and that interaction effects evolve over time rather than occurring instantly. In addition, both papers demonstrate that simplified assumptions, such as isolated foundations or ignoring groundwater effects, can lead to unconservative designs. These case studies highlight several important lessons that are directly applicable to engineering practice, particularly in dense urban environments. One key lesson is that foundations should not be analyzed as isolated systems when nearby construction is anticipated. Both papers show that adjacent buildings or excavations can significantly alter the stress distribution in the soil, leading to settlements that are much larger than those predicted using traditional isolated foundation assumptions. Another important takeaway is the role of groundwater behavior. The deep excavation case clearly demonstrates that confined aquifers can dominate settlement mechanisms, sometimes to a greater extent than soil stiffness or retaining wall performance. If groundwater drawdown is not properly accounted for, even advanced numerical models can substantially underestimate ground and foundation movements. These studies also reinforce the value of field monitoring. Instrumentation played a critical role in identifying unexpected behavior, confirming governing mechanisms, and guiding back analysis. Monitoring is essential not only for construction safety, but also for improving the reliability of analytical models in future designs. Both papers emphasize that simplified analytical approaches can still be extremely useful. When applied conservatively, simplified methods such as interaction factors or screening level analyses provide engineers with practical tools for early decision-making and risk assessment before resorting to more complex models. What I found most interesting in these studies was how significant interaction effects can be compared to what is commonly assumed during routine design. In the Poulos paper, the fact that settlement of a building nearly tripled due solely to the construction of surrounding buildings was particularly striking. The central foundation itself did not change, yet its performance deteriorated dramatically as nearby foundations were added. This highlights how misleading it can be to evaluate foundations in isolation when development occurs in phases. This study also connects directly to how an individual pile behaves differently from a pile group. In practice, individual piles are often designed assuming uniform stress distribution and limited interaction with adjacent elements. However, once piles act as part of a group or are influenced by nearby groups, their behavior is governed much more by group stiffness, load sharing, and interaction through the soil. Poulos' equivalent pier approach effectively captures this concept by treating the pile group as a single system rather than a collection of independent piles. The paper reinforces that pile capacity and settlement behavior cannot simply be scaled up from single pile behavior without considering group effects and external interactions. In the deep excavation case study, what stood out most was that groundwater drawdown had a greater impact on bridge pile settlement than soil deformation caused by excavation alone. This reinforces how dominant groundwater conditions can be, especially in layered soil profiles with confined aquifers. It also illustrates how pile foundations that may appear adequate under static conditions can experience accelerated settlement when hydraulic changes occur nearby. Both papers strongly connect to course concepts related to soil-to-structure interaction, staged construction, and the limitations of simplified assumptions in geotechnical design. They demonstrate that foundation performance is often controlled by time-dependent processes and construction sequence rather than by final loading conditions alone. Overall, these case studies reinforce the importance of thinking beyond individual elements such as a single pile or a single building, and instead evaluating how foundations behave as part of an interacting system within an evolving construction environment. This semester has taught me a great deal about the design and performance of both deep and shallow foundations. Thank you for watching.